Okay, we have a beam balanced on a domino here. And you're going to I'm going to figure out which way to do this. Without my arm's too much in the way. Okay, I've got a marble on this end. I've got a steel ball. Marble has a little bigger diameter than the steel ball, but they're fairly comparable. And people will generally tell me that, well, then the steel ball is probably going to be more massive. And it certainly is. To the extent that if I put the steel ball here and release this end, it's going to balance that. It's going to go that way. Okay. Now, if I put the steel ball here and and now things just slid. Steel ball here and remove the force from this end. It goes down on this end. But somewhere about here, the thing stays in balance. Now we can find that point, but it's a little tricky to keep things from rolling and messing everything up. You get the idea. And we made a fairly decent observation that the mass of the steel ball, or that the steel ball balanced when it was about 3 times closer to the center of mass, or to the balancing point of the beam, than the marble. Okay, which tells us, pretty intuitive, people came up with it right away, that steel ball is probably 3 times as massive. Now we're going to pretend that this thing is balanced and we've got the marble here and the steel ball here, and the balancing point is about here. Okay. Then if I move the marble at a constant velocity of, say, 8 centimeters per second toward the steel ball, well, what's going to happen? If this thing's on the fulcrum, it's going to tip that way. To prevent that, I would roll the steel ball toward the marble so that I'd have them both moving. Okay. And I ask, how fast should the steel ball be moving? If you know the speed of the marble, how do you find the speed that the steel ball should be moving in order to keep this thing in balance? Okay. And people came up with the idea, well, the marble should be moving 3 times as fast as the steel ball, because intuitively, it appears that that would keep these things at the same relative distance from the center. And it turns out that's right. Now, right now, people in the class are writing out their argument to show that that's so. And then somebody said, very perceptively, if I apply the same force to both of them, that would, in opposite directions, that would accomplish it. Okay, then, well, forces with acceleration times squared. Does that really work? And that Zoom is getting really jerky here and it keeps crashing. So let's hope we keep going here. Turns out that does work, so I ask why. Okay, and I got the answer, well, because acceleration is inversely proportional to mass. Well, that might make sense, but that won't make sense to everybody that hears it. Okay. But I said, well, if you got 1/3 the acceleration start from rest, does that mean that it's going to work? Well, people are writing out the answer to that, but we'll write it out on the board shortly once we see what people think. Okay, so I don't know if I've even, yeah, I've got it. Okay. So here's a beam. Unfortunately, magnets are kind of black, so they don't show up real well against the blackboard, but fair enough. Here's the approximate balancing point. Now, if it's like this is at equal distance from the balancing point as this one. So it's not going to balance. If I lifted this up at the balancing point, it would tip over that way. As we've seen, since this has 3 times the mass, it needs to be 3 times as close to the center in order for the thing to balance. Okay. So one thing we can do is we can draw a little picture here. Here's our balancing point. And here is one mass, which is 3m, and another mass, which is m. I'm going to call this distance x1. This distance x2. So m1 is going to equal m1 is going to equal 3m, and m2 is going to equal m. That picture makes sense in terms of what we just saw. So, yeah, good. Using hand gestures the way I'm recording, that's great. Got some interesting hand gestures there, not nice variety of hand gestures, all of which are saying, yeah, okay. Okay. Our condition here is that m1 x1, I don't like the way I did that. X1 is going to be a vector. It's going to be directed in this direction. X2 is going to be directed in this direction. Okay, I'm going to say that m1 x1 plus m2 x2 equals 0. Now, because of the arrows, x1 and x2 are in opposite directions. So one of them is positive and the other is negative. So that when I add them up, I can get 0. Okay, so this is actually the condition for rotational equilibrium of this beam. Now this beam's in rotational equilibrium because it's sitting on a flat surface, but before I did have the magnet or the domino under here, and we saw the balance. Okay. So now what we think is, well, it can be summarized like this. We think the proportionalities. The distance of one of these or the other is inversely proportional to its mass. That was the first intuitive step. That's pretty much what you were thinking, wasn't it? Just an inverse proportion. This tells you the same thing. This says, if you solve this equation, you can rearrange it to say x1 over x2 equals m2 over m1. Put absolute value signs around the x's. So I don't have to worry about the negative. Just when thinking about the proportion, this is the ratio of the x's, this is the ratio of the masses. They're an inverse proportion. Okay. Now we said, okay, now if this is a ball and this is a ball, I roll this ball this direction and it's in balance, then it's going to tip over that way because this ball is going to be exerting less rotational effect than this one. We call that torque. We'll define that in a couple of weeks Right now, we'll just be intuitive about the rotational effect. Okay, it's just the product of the mass and the distance, and that really is a torque. You know what torque is, you can think in terms of torque. Okay, so anyhow, this thing will have less distance. So if we move M1 closer, M1 X1 gets smaller. And this stays the same, so they're not going to be equal to, they're not going to add up to zero anymore. Okay. Well, the next thing we thought is, the way I've labeled this corresponds to the way it was when I was standing back there looking at you. I haven't used the fact that this is 3M and this is M. Bad looking 3 on me, which I should have anticipated. Okay. Actually, I did anticipate it, I thought I could handle it. Okay. So I'm going to make this one 3M just because it corresponds to the order in which you see them. So you don't have to keep switching arc plots. Okay, so I'm going to say now, if M1 moves towards the center, move toward the center at a third the speed in order to maintain equilibrium. Okay. And that's true. And you can prove that. I'll leave it to you to figure out how to write that out. Okay. I could write it out. I'm going to do a lot of things today. I want to give you a start on the stuff you're going to need to do in the first assignment, chapter 8. Okay. Boy. Okay. Then we got a conjecture. We got these conjectures very quickly, and they were very good. Okay. I said equal and opposite forces. I should have said equal and opposite net forces. So that little thing I inserted there is the word net. Equilibrium will be maintained. Now, there's a qualifier in that. They've got to be initially at rest. Okay, so initially at rest, or if you wish, initially moving, so this one has a third the velocity of this one, both toward the center, or away from the center as far as that goes. Not talking about away from the center because the thing ends here, and that wouldn't be practical. But if there's a long balancing, they could be moving either way. Okay. So equilibrium will be maintained. I'll say the argument for that is The acceleration of M2 will be a third that of M1. Okay. Now, that's not direct. That's not the reason. You got to think what the acceleration will do to the velocities. But if the acceleration always induces a third the velocity on this one, it does on this one at every instant, then it's going to stay in equilibrium. So a lot of insight there. And the first exercise in chapter 8 seems to have nothing at all to do with the subject of chapter 8, which is impulse and momentum. Has everything to do with it. Okay. There's an important condition on impulse and momentum, and that's what we're going to talk about in a minute. Okay. But this situation should get you a start in understanding what's going on with that first set of problems, which is pretty much unlike the rest of the problems. So if you get messed up on that one, go to the rest of the problems, start working them, and then come back. Okay. Make sense? It's just because if you get messed up on the problems that have to do with this kind of situation doesn't mean you're going to be messed up on the next set of problems or the very next problem. Okay. Okay. Now we're going to talk about impulse momentum. That on. Okay. And what I just said is you should be familiar with all this. I ask you to derive it in a test, you should be able to. I wrote it down kind of quick and kind of small, so some of you might have trouble seeing it, but it's just, you got your VF squared equals V naught squared plus 2A delta X, and acceleration is F net over M. Then you plug that in for the acceleration and rearrange it, and you get your work energy theorem, F net delta X equals delta K. Okay? That should be second nature. You have to know where that comes from to understand how everything fits together and to understand what I'm about to tell you, which is that also VF equals V naught plus AT, right? And A equals F net over M. So finish it for me. If I can find a decent piece of chalk, I'll do it. Okay. So we have this, and A is F net over M. So we have VF equals V naught plus F net over M P. Well, that's analogous to what I did here, right? What I do next? Got rid of all my denominators, among other things. Okay. So get rid of my denominators, multiply by M. And when I rearrange it, I can get F net P equals M VF minus M V naught. Now, instead of T, I'm talking about a delta X here. Really want to talk about a delta T, a time interval. Something that happens over some time interval. You'll see what it is in a minute. And I get this. Okay. Well, this is your work energy theorem. And this is your impulse momentum theorem. But in the context of calculus, since F net is not necessarily constant, your work energy theorem instead of a constant f net times the delta x, you integrate f times dx. Okay, over some interval, say from xi to xf. And that's the way it's derived. It's derived in your textbook. And when I took the course, I found that derivation a little tough to understand. Okay, so you might have found it the same. But it's worth looking at. And then the derivation of this, which is impulse momentum, which is the integral from Ti to Tf of f dt equals delta P. Make it a little more complete. The work energy integral is a dot product of f with a dx. And that's why I use a ds. Because it's not always, you're not always moving in the x direction if you're in the plane. Okay. And if we're following a curve, well, you don't know what to do if you're following a curve. You learn that along about 1st of February. Okay. And probably calculus or vector calculus 3, whatever we call it these days. Okay, so it's f dot dx. It's been called those same things. It was M3 when I took it. Okay, M1, M2, M3, M4, because everybody took the same 4 courses. F dot dx. Okay, that's a dot product. So you do end up with a scalar quantity, right? Just a number with some units on it. And units are going to be joules, or kilogram meter squared per second squared, or ergs, or whichever. Okay. Impulse momentum theorem, it's f dt, but f is still a vector, and dt, it's not a dot product. Okay. So what you get over here is a vector. Delta P, where P is MV. Vector. Okay. This, you have 1/2 m Vf squared minus 1/2 m V naught squared. And 1/2 kinetic energy is 1/2 mv squared. This is a scalar quantity. This is a vector quantity. You want to be sure you understand that from the very beginning. Okay. This is what happens if you exert a force through a displacement or over some path. Okay. You get the change in kinetic energy if you do this interval. Here, you're exerting a force for a time, which is different than exerting a force for a distance. Okay. Force is a function of position, but force is also a function of time if you're moving. So those are kind of important things to understand. Now, the idea of momentum is pretty simple. It's just mass times velocity. Well, I found out the other day that in my prime, I could do more pull-ups than Cole can. Okay. Of course, Cole weighs about 1.7 times my prime weight. So I don't know, does that make him stronger? I don't know. He looks like he might be almost as strong as I am now, but I don't know about in my prime. Okay. Yeah. So let's use our imaginations and imagine me in a suit of armor or something running down a football field, running into Cole, who's also running toward me. Okay. Now, suit of armor or not, I'm not going to match his mass. Okay. And I can't move as fast as he can. I mean, fast walk will beat me. Okay. So, I don't even know if I do it. Yeah, well, when we collide, let's just say we're moving at equal speeds and we collide right here. Which way am I going to be moving after collision? That way. Which way is he going to be moving after collision? He's still going to go forward. He's not going to stop. He'll slow down. Unless he decides to throw a shoulder or somehow increase the impact at the moment of, okay? So, if I'm still alive, I'll be able to analyze it. Okay, well, that's a function of momentum, not energy. Okay, as a matter of fact, the total energy of the two of us after collision is going to be less than it was before collision. Okay, now there's a thing called a perfectly elastic collision. Imagine two pool balls on a frictionless surface. It's pretty close to a perfectly elastic collision. Okay, where all the kinetic energy is conserved. If I'm running towards somebody of the same mass, we're going to lose all our kinetic energy if we're moving at equal speeds. Okay, I might have more damage than the other person will due to my tendons and ligaments being a little tighter. Okay, and other factors. But we'll still come to rest. I might drop into a mangled heap and the other, just standing grinning. But we'll still come to rest. And that illustrates that you don't have to conserve kinetic energy. Right? Now, if we're both encased in a big old bouncy ball and take a flying leap, we'll come off. We might come back with appreciable proportion of our initial kinetic energy. We're probably going to lose some because that ball produces heat when it flexes and stuff like that. A pool ball does the same thing, but it doesn't flex much. Okay. So those are important ideas. Okay. So momentum kind of governs collisions. Kinetic energy, you can't assume anything about kinetic energy unless you decide that the collision is either perfectly elastic or kinetic energy is conserved, or perfectly inelastic where the two objects stick together or move off at the same velocity. Okay. So if I run into the big guy here and he just decides to grab me and keep moving, okay, he's going to be moving slower and I'm going to be moving slower. So our total kinetic energy is going to be less. And that's actually the minimum kinetic energy that can come out of that collision. Now, hopefully that makes sense. I had a question here, so let's see what it was. Okay. Here we have a mass, make it the shape of a ball. M1 moving at velocity V1, M2 moving at velocity V2. Okay. So what's P? Well, what's the momentum of the first? Oh, well, right there is the definition of momentum, right? Yeah, P equals, okay, this is P total. M1V1 plus M2V2. Let's say these balls collide. Now, what happens when the balls collide? The balls are in contact, and these colors. First ball exerts a force on the second ball. Call that F12. And the second ball exerts a force on the first ball. Call that F21. So the acceleration of the first ball is the force exerted by the second ball on the first divided by the mass of the first, right? And the acceleration of the second ball is the force exerted on it by the first ball and let me reverse my colors here. So that F12 is always green, or F21 is always green, and F12 is always purple. And you think about the colors and stuff, you don't really even need them. But we have this. Okay. We're not actually going to use the acceleration. We want to be aware of this so that the change oh yeah, the other thing is the reason I did this. This is the contact force. Okay. If I'm on a skateboard, big guy is on a skateboard, and I push him, he's going to go that way. And I'm going to go that way about 1.7 times as fast. Okay. Actually, I've lost weight. It's more like 1.8 something. All right. The reason for that is if I push him with a force of 10 pounds, don't want to hurt him. Okay. Push him with a force of 10 pounds. Well, he's not doing anything, but I'm compressing, let's say, his shoulders, which are then trying to decompress. They're pushing back with a 10-pound force on me. Okay. Equal and opposite forces. Now it's Newton's third law that you know about. But there's our first real application of it, I think. This is Newton's third law. It follows that the accelerations are inversely proportional to the masses. So that the changes in velocity will be inversely proportional to the masses. Okay, well, let's see what impulse momentum theorem says about this. In an isolated system, are the only forces they're equal and opposite. The changes in momentum are equal and opposite. Now, why is that? It's because impulse momentum theorem, and these should all be net forces. I'm careless with that. As far as the first ball, the change in momentum is just the integral of F net dt, where F net is the force exerted on it by the other ball. Why is this? Well, it's because delta P1 is the integral of F12. It's F21. Okay. It's the integral of force exerted on it by the second ball. Or is the second ball on the first? Okay. This is the force exerted in the first ball by the second, and F12 is equal and opposite to F21. So that's the relationship between the integrals. So the changes in momentum are identical. Equal and opposite. It might be hard to read, but from this, it's clear if you add delta P1 to delta P2, you're going to get zero because they're equal and opposite. And that's the change in your total momentum. And that's conservation of momentum. So from the impulse momentum theorem, you get conservation of momentum. Now, there are often in a system more than just two masses interacting. But however many you have, they're always exerting equal and opposite forces on one another. And when you add up all the equal and opposite forces times the time interval, you're going to get zero. So there's no change in the total momentum of an isolated system. Now you have to learn about what isolated systems are and so forth, and your materials will clarify that for you. And we can clarify it in class if necessary to do more. Okay, well, let's do a simple example. Let's say that our steel ball and our glass ball collide. Let's go back. This. Now, we're not going to assume that this is moving at 1/3 the velocity of this one. Just whatever two velocities. So we're moving these along a track, we're colliding them, and we're seeing what happens. The total momentum before is M1V1 plus M2V2. And total momentum after, we're going to say is M1U1 plus M2U2. Then M1V1 plus M2V2 equals M1U1 plus M2U2. All velocities are along a straight line, like two balls on a track. They're confined to one axis. And we can write it like this without the arrows. With the understanding that B1 and B2 and U1 and U2 could be positive or negative depending on the situation. And the positive and the negative take care of the vector nature of the forces or the momentum. Okay.
This is the route that was built on its listing. Illegal.
For centuries. And return to Alabama.
The next part of the don't know much about it.
Okay, so what I'm saying is, glass ball has initial velocity of 20 centimeters per second, steel ball negative 10 centimeters per second. Afterwards, glass ball's moving backwards at 5 meters per second. Okay.
Says he could see right away the shipwreck was too big.
Well, you could write out this equation, right? So what do you get if you plug numbers into the equation? Now for M1, you're going to use M. For M2, you're going to use 3M. How many unknowns are you going to have left? It's going to have one unknown. And which one's that going to be? It's going to be U2, right? So it's going to be easy to solve the equation. So just write it out. Start solving it. I might not give you time to finish solving it, but it's easy equation. Everybody will be able to solve it. Okay, so you're going to have this. This is before collision, right? Actually, everybody's pretty much got that. I don't like the way you guys keep suppressing units. Not I'm going to punish you for it, but you're going to screw up sometime because of doing that. So try not to. Anyhow, you're then going to have this. Okay. Now you solve for U2. Maybe get this over there and stuff like that. And one thing I can do with my units on the left-hand side is going to say, okay, I'm going to have 20M minus 30M plus 5M centimeters per second equals U2 times 3M. I factor out the centimeters per second, so everything that's going to end up on the left-hand side is going to have that unit, right? Now I've got M, but M divides out. Okay. Twenty minus 30 plus 5 is minus 5. Over 3 centimeters per second. Okay. I could have divided out U at any point. M could have divided out the mass M at any point. Could have divided it out before I got to here, so we wouldn't even have to have the M's. But that's what we come out with. Okay. Now, what the change in velocity of each ball? Well, we only got a minute, so I'll do it for you. Final velocity is -5 centimeters per second minus the 20 centimeters per second, which is -25 centimeters per second. I mean, think about it. It's moving 20 centimeters per second this way. Now it's 5 centimeters per second this way. It's lost 20 and then another 5 in the same direction. So that works. Still, change in velocity is final velocity, which is -5/3 centimeters per second minus 10 centimeters per second. And this isn't working out. It's minus negative, and that's why. Okay. So that is 5/3, 5/3 and 50/3 is plus. It's not 50/3, it's 30/3. At 25/3 centimeters per second. And it's pretty clear that 25/3 is 1/3 of 25, right? So it's plus, this is minus. 3 times the magnitude here is here because this has 3 times the mass. That's 3 times the effect on the velocity of this one that this does on this one. And that comes back to impulse momentum theorem. And you could have done that with the impulse momentum theorem initially, but we're out of time, so that should get you a start.